Reza, represented by Ali Basari from Shiraz University of Technology, Iran, to give a wonderful poster presentation entitled Comprehensive. Oh, sorry. Am I reading the? Can you go back to your title?
Uh-huh. Sure. Yeah.
Okay. All right. Yes. Thank you. Okay. So the Professor Ali Reza is going to present on the title "Exploring the Potential of MQP Sequences in Terahertz Photonic Crystal Media with High Temperature Nanosuperconductors." Doctor, the floor is yours.
Thank you. Thank you for your introduction and thank you for having me in this conference. It is my pleasure. Uh, Let me just zoom in on the introduction. Yeah. Uh, Hello, my name is Ali Basri from Shiraz University of Technology. Today I will briefly introduce our work on designing ultra-narrow terahertz filter using mid-quasi-periodic sequences photonic crystals built from high-temperature nanosuperconductors. One may ask this question, why this problem matters? The terahertz band is actually rich with applications in imaging spectroscopy and especially telecommunications and highly selective filters superconductors, especially nanosuperconductors layers, also offer very low loss and strong interaction with terahertz photons and using high temperature materials such as actually mercury, barium, calcium cuperoxide, and bismuth, strontium, calcium cuperoxide, which could be represented as Hg1212 or Bi2223. Let us operate with practical cooling, making devices more feasible outside the lab. What we did here, as you can see in the introduction, uh, is that actually we modeled a one-dimensional multi-layer photonic crystal composed of alternating superconductor and dielectric films. The superconductor's permittivity were computed with the two fluid models, which I actually uh, explain you in further section in detail to capture temperature and frequency dependent superfluid and normal component. And we finally calculated the transmittance spectrum or profile of the one-dimensional, the proposed one-dimensional photonic crystals using transfer matrix method for both TE and TA polarization. The novelty of our work is that instead of purely periodic stacks or arrangement, we used mixed quasi-periodic arrangement, or in abbreviation, we can say MQP arrangement, which is the combination of Dumor's sequences, Cantor, Fibonacci, and periodic doubling sequences applied to different layer groups. This actually deterministic mixing creates richer spatial interference inside the one-dimensional photonic crystals, which we exploit to achieve photonic band gaps and actually terahertz photonic band gaps, and to reproduce extremely narrow Dirac delta-like transmission peak. So the key results here is that we actually proposed a photonic media, a layered media that the transmittance spectrum that which is the outcome of this structure could be tuned by several parameters like sequence order, lattice constants, incident angle, and temperature that we actually uh, at the end generate a single highly tunable transmission peaks around around 8.8 to 9.5 terahertz, and showed a predictable peak stacking behavior as actually total period number increases. Now let's go to the nitty-gritty of the methods. The method actually we utilized here is two-flight theory, transfer matrix methods, and the mixed quasi-periodic sequences or concepts that uh, have been utilized to engineer or design these one-dimensional photonic crystals, nanophotonic crystals. Uh, before explaining about the superconductors, that why we use these actually sort or type of superconductors, let me explain about the two-fluid theory that you can relation one here that represents for permittivity of our superconducting layers for both Hg1212 and Bi2223. The two-fluid theory actually models the charge carrier below critical temperature as two existing components. A superfluid component that flows without resistance. We have, in other words, we have two types of carrier uh, or electrons that the first actually groups flows without any resistance, and the second category is the normal component that exhibits ordinary dissipative behavior. So the normal component electrons are responsible for our damping parameter here, which evidently shown in relation 1. Uh, Actually, the electrodynamic response is expressed as a complex dielectric function that you actually see here. This actually relation could be expressed as a relation that uh, consists of a real and a complex actually section or part, whose real part actually comes mainly from the superfluid response, as I just said, and whose imaginary part actually accounts for dissipative absorption by normal carriers. Simply put, two-fluid actually forms the superfluid contribution appears through the uh, sorry appears through the London penetration depth and gives a frequency-dependent inductive term. The normal part is commonly modeled with damping term with sets which actually sets the loss here, which represents here as gamma. And The second actually method that we utilized here, as I said, is transfer matrix methods, or TMM. What actually do for us, it actually does for us, is that it relates the electromagnetic amplitudes from one side of our uh, photonic constructions to the other side. In other words, in this actually method, we can correspond the each layer of our construction to a transfer matrix method. And by multiplying the the transfer matrix for each layers, we can actually uh, reach or achieve a total transfer matrix, which actually give us the transmittivity and the reflectivity. So by means of this transfer matrix method, we could actually yeah, calculate these two quantities without going to the more complex methods like if FDTD or RCWA, which are so complex rather than transfer matrix methods. And the other concepts that we need to know for studying the proposed photonic crystal is mixed quasi-periodic sequences, which it actually uh, offered in 2020 in Journal of Applied Physics. It actually simply tells us that if we combine two types of quasi-periodic arrangement, like for example Fibonacci or Dumors or Cantor, we could actually uh, maintain or reach a uh, bigger or superlattice as what we actually see here at the bottom. If you see the construction vividly here. So by means of these arrangements, we actually engineered or uh, construct our superlattice that gives us these transmittance profile here. In the first uh, diagram, as you can vividly see, we have frequency intervals versus transmittance. These peaks are responsible for our transmittance peaks, and these gaps actually represents for the frequency intervals that suppress our transmittance here. So in these special frequencies, we have transmittance peaks, and we in betweens we have actually nothing. It actually filters some special frequency for us. And more, uh, if you actually explain in detail, we can say that if you consider actually this transmittance peak shift to actually higher frequencies as we uh, increase the incidence angle. If we actually uh, emit the beam of incidence in a angle rather than the normal incidence, and actually gradually increase this angle, we see that these transmittance peaks move forward here. This is just for considering the periodic arrangement, but our main actually discuss is over mixed quasi-periodic arrangement here. That as you can see uh, here, we actually utilized the second order Dumor's sequence and the first order triadic counter sequence in the under some circumstances that explained in detail in the article. As you can see, this actually condition yields a remarkably different transmittance profile with potential for diverse application in this actually configuration. First order Cantor and the second order Dumor's sequences are combined, producing a transmittance spectrum characterized by actually recurring well-defined peak pairs. As you can see here, this is a pair of our transmittance peak, and this is a stack of transmittance peak. Actually, yeah, the well-defined actually peak pairs at specific frequency point. These pairs exhibit a degree uh, of sorry a degree of tunability in state A. The peaks are sharp, and their separation increases with frequency from approximately 1 terahertz for pair actually 1 to about 0.5 terahertz for pair 9 here. Increasing the incident angle in the TE mode progressively sharpens these peaks as observed from the state A to D. Yeah, as if we actually magnify these stack of transmittance peaks, we can observe that there are several separated transmittant peaks in these stacks that form a pair or stack here as we actually towards through state A to D, these actually transmittance peaks become sharper and sharper. And this actually condition is the most accelerating condition and circumstances that we were looking for. In this condition, we actually utilized the second order of Dumors and the first order periodic counter sequences. In this condition, we actually observe that nearly all wavelengths are suppressed, as you can see, from 0 to around 10 terahertz, and from around 11 to 15 terahertz. And allowing a transmission only within a very limited frequency intervals, as you can see here, the transmittance peaks often reduced to a single narrow peak. This peak is tunable as demonstrated by its systematic shift with increasing incidence angle from state A to D here, as you can see. Notably, in the TE mode, state A, increasing theta or angle of incidence results in a single transmittance peak that closely resembles the actually profile of Dirac-like function, as you can see here. The transmittance peak is too much narrow, ultra narrow, like a Dirac delta functions. And conversely, in TM mode or TM polarization, and anticipated as actually we anticipated the mode, the TM mode actually peaks broaden with increasing, uh, sorry, yeah, with increasing theta here, and finally in the you know last circumstances, we actually utilized here the fourth order of Fibonacci and second uh, periodic doubling sequences. The rest parameters like temperature, angle of incidence, lattice constants, the total period number are the same. But the only thing that actually changed here is the MQP sequences. Here we actually use fourth order of Fibonacci and second order of periodic doubling sequences here. Again, all of the frequency, all of the actually transmittance profile, the transmittant peaks are suppressed here, and it actually only let one single transmittance peaks to be transmitted here, as the outcome, as our photonic outcome. And to sum up, I actually, can say that in this study we actually demonstrate that mixed quasi-periodic layering that combines Fibonacci, Dumors, and Cantor, and periodic doubling rules allow precise sculpting of photonic band gaps and transmittance spectra in one-dimensional superconducting dielectric photonic crystals by tuning lattice constants, periodic number, incidence angle, and actually temperature and normal electron damping. Mixed quasi-periodic actually architecture produced Dirac delta-like peaks and controllable stacked actually resonances, ideal for ultra narrow terahertz filtering using high temperature superconductor, reduces cooling needs, and minimizes losses, making these high quality structure practical for terahertz communication, imaging, and sensing. That's all of my representation. Thank you for your attention.